All right. Good afternoon. Welcome back. Hope everybody had a good spring break, and just picking up with once again functions. And in chapter two, okay, we have the first section. Okay, is going to concern quadratic functions, and we have encountered quadratic functions in various capacities, like working with the quadratic equation and working with the quadratic formula. That is the case of working with quadratic functions. Now, for a formal definition of what we have regarding quadratic functions, okay, we have by definition, okay, quadratic function is a second order function whose standard form is y is equal to f of x is equal to ax squared plus bx plus c, whereupon a does not equal to 0. Okay, so it's kind of like what we have with the quadratic formula. So again, just emphasize. Okay, so quadratic function, okay, that is a second order function, and the second order in reference to the x squared. Okay, and again, this particular layout, okay, is going to be the standard form. And in the first section of chapter 2, it's going to go into a different way of expressing quadratic functions. Now, in terms of working with quadratic functions in general, I normally go with the standard form, but the first section, okay, mentions another approach, and this is going to be what is regarded as the vertex form. And for what we have in the case of what's going to be regarded as the vertex form of a quadratic function, okay, it's going to be a different way of expressing the same thing, and I am momentarily going to abandon the standard form of a quadratic function and focus on the vertex form. But again, we'll be looking at toward the end a case of translating between the types of expressions to which a quadratic function is going to be defined. Okay, and now for what we have in the case of the vertex form of a quadratic function, okay, so we're still looking at the same y and f of x. Okay, so you have y is equal to f of x is equal to a times the quantity of x minus h raised to the second followed by the addition of k. Now we're still looking at the same y, the same f of x, the same letter a, but where we had bx and c, okay, then we had the letters h and k to sort of take their place in the layout. But again, we'll look at a translation between how we go from these terms in a, b, and c to what we have in a, h, and k. And first of all, for defining features of the vertex form of a quadratic function, again, we have the leading coefficient is a. And there's some things about a, the significance of this. Okay, now a is non-zero in value. Okay, so that, and a is a real number, and it could be either positive or negative. Okay, and if a is positive, then the graph of f of x is going to open upward. It's going to open up. Okay, and what's it going to open up from? It's going to open up from a point that's referred to as the vertex. And the vertex is going to be an ordered pair, and this is where we're going to have the letters h and k to come in. And on the other hand, again, a is non-zero in value, so either it's going to be positive or it's going to be negative. And if a is negative, then you're going to have the graph of f of x to open down from the vertex. Okay, vertex is still going to be h and k. And we'll be referencing like either the minimum or the maximum. Now, the other week we looked at terms like relative minimum, relative maximum, and in the case of quadratic functions of this type, okay, the vertex is going to be binary. Either the vertex is going to be the maximum or it is going to be the minimum. Okay, and now regarding a, okay, so this is just a variable. Okay, once you translate into specified value, this is just going to signal how the graph is going to open. Now, where h comes in, h is going to serve a bit of a twofold purpose. Okay, and one is going to be what is regarded as the axis of symmetry. And the axis of symmetry, okay, that is in general format. We have the axis of symmetry, x is equal to h. And what this is going to be, it's not going to be the graph of the function itself, but it is going to serve a purpose, like in terms of keeping things proportional. And this is going to be a visual vertical line. That's going to divide it's going to divide the graph of f of x into equal halves that will mirror each other. So we have into equal mirroring halves. Yeah, so the axis of symmetry, you have a visual vertical line that divides the graph of f of x into equal mirroring halves. And the other role that h plays is along with k, and that is going to be in the formation of the vertex. And the vertex, okay, had the order pair hk, and that is going to be the point from which, okay, the graph of the quadratic function is going to open. And to think about the graph of a quadratic function, there is a name for this. Say, like if it's opening upward, it would be something like a hybrid between the letter U and V, the letters U and V in appearance. Okay, so we have for the graph of a quadratic function, okay, that is a parabola. And just kind of drawing out some of the general cases. Just kind of a quick overview. And just doing kind of a little bit of a quick sketch. Okay, so you have like the graph of a quadratic function. Okay, so again, ax squared plus bx plus c, that is the standard form. And again, just for the vertex form, you have a times the square of x minus h, followed by the addition of k. All right. Okay, so just for what we have here. Okay, so the graph is opening upward. Okay, so this means we have in this scenario with the letter A. Okay, so A is positive. And because A is positive, okay, now the graph of f of x opens up and it's going to open up from the vertex hk. And if you notice, okay, we have with the vertex hk, that is going to be the bottommost point of the graph of this particular quadratic function. And because of the location, okay, now the vertex is going to be the minimum of the function because it is the bottommost point. Okay, so this is where the vertex is going to be the minimum. And then slightly switching gears. Okay, so I'm just going to keep what I have as it is, and I'm just going to add in this little detail here. That red line that passes through the vertex, okay, that is, again, that's going to be the axis of symmetry. So I'm just going to use AOS, short for axis of symmetry. Okay, so that's going to be x is equal to h. And the axis of symmetry always is going to pass through the vertex. Okay, again, x is equal to h, and your x value is already at h at the vertex. Okay, now for what we have now, see if I change the direction. This time we have f of x. The graph is going to be opening downward. So we have in this particular scenario, okay, so we have f of x is going to be negative. And with a being a negative value, okay, this time we're going to have that f of x is going to open downward from the vertex. And notice, okay, this time it's binary, okay, so here before the vertex is the location of the minimum. But now with the graph opening downward, okay, the vertex point is at the top, so the vertex is going to be the maximum. Okay. Again, still had the same axis of symmetry. Okay. So you still had the same general form for the quadratic function. Still might have the same location for the vertex, but where it is relatively speaking, with respect to the rest of the points that make up the graph of the function, again, the vertex is either going to be on the bottom or on the top. Okay, so So here in this case, the vertex is the minimum, and in the second case, the vertex is going to be the maximum. Now, let's say that in looking at a numerical application, and let's say that if we have a function that is provided in vertex form, and let's say that let's say we have given f of x is equal to, let's say, the square of x minus 2 followed by the addition of 5. So if we were to determine the following, okay. So we have the direction that f of x opens. And we have the axis of symmetry. And once again, identify the vertex. Okay. Again, this function is provided in vertex form. So just looking at the components, okay, just the general layout for the vertex form, you have f of x is equal to a times, okay, the square of x minus h followed by the addition of k. And for what we have specifically, we have f of x is equal to the square of x minus 2 followed by the addition of 5. Okay, and okay, so the ingredients for finding out the direction, the axis of symmetry, and the vertex, we're looking at identifying or evaluating what a, h, and k are going to be. Okay, so if you notice, we don't have any number explicitly in front of the square of x minus 2. Okay, so this, just read this. Just read this as if it were 1. Okay, so you have 1 times, okay, the square of x minus 2 followed by the addition of 5. So a is going to correspond to 1. Okay, so you have a is equal to 1. So you have that a is positive. And since a is positive, if the leading coefficient is positive, that means that f of x is going to open upward. Okay, now in terms of finding out what h and k are going to be, let me mention something. Okay, first of all, the graph does open upward, okay, and that's contingent upon the sign value of the leading coefficient a. Now for the axis of symmetry, okay, remember we dealt with, this is going to originate from the x minus h portion. Now we're not using the zero product property per se, but envision this like taking the expression with the x in the parentheses and setting that equal to 0. So you have like, so if you take x minus h, set equal to 0, and you have the x is equal to h. And again, so you had the axis of symmetry, which we're going to have at x is equal to h. Now, for what we have here, x minus h is going to be represented by x minus 2. So So you have x minus 2 is equal to 0. And so we have that x is equal to 2. So that's going to be your axis of symmetry. So your axis of symmetry, you have like x represents h. And for that value h in this specific instance, okay, that is going to be equal to 2. And as for the k value, okay, you have the addition of 5 to follow. So you have that k is equal to 5. So h is going to be at 2, k is going to be at 5. So you have for the vertex hk, we have the location at 2, 5. Okay, so the graph opens up. The axis of symmetry, again, is going to be x is equal to 2. And the vertex, okay, we have, that's going to be the minimum point since the graph is opening upward. And so the vertex we have at 2, 5. Okay, now, just looking at what we have. Regarding the behavior of this function. Okay, I already had this one. So I'm just going to mention, okay, so you had the graph, okay, you have y is equal to f of x is equal to the square of x minus 2, followed by the addition of 5. Okay, so this quadratic function, its graph we have in green. Now if you notice, you have a line that's running through the middle and passing through the vertex. Okay, and again, just for this vertical line, it's not part of the graph of the quadratic function. It just evenly divides up the graph. Okay, so again, you have the axis of symmetry. And that is that x is equal to 2. And once again, we have with the vertex point. So the vertex we have at 2, 5. And everything in the quadratic function is above this. And so this particular vertex, okay, that is going to be the function's minimum. So the vertex is going to be a minimum. Okay. Now, let's say that if we have another scenario, and let's say that if we have f of x is equal to, let's say we have negative 2 times the square of x plus 5 minus 10. And say if we were looking at trying to find the same three components where the graph opens, the axis of symmetry, as well as the vertex. Okay, so just once again adopting the general layout of the vertex form. Okay, and if we go ahead and identify a, h, and k, all right, so we have for this particular quadratic function, we have that a is equal to negative 2, so a is negative. And again, with a as a negative value, okay, we're going to have the graph to open downward. And again, corresponding to h. So we have x minus h is represented by x plus 5. And with setting equal to 0, the binomial x plus 5, okay, we'll have the x is equal to negative 5. So you have the x is equal to h is equal to negative 5. So the axis of symmetry is going to be at x is equal to negative 5. And in terms of what we have with the k value. Okay, so for this function we had the subtraction of 10 at the end. Okay, and so we had that k is equal to negative 10. Okay, so pairing that up along with x equal to, or h equal to negative 5, we have the vertex with the coordinates negative 5, negative 10. Now, just looking at what we have for this particular function. Okay, so you have for this quadratic. Alrighty. Okay, so I have say I have f of x or y equal to negative 2 times the square of x plus 5 minus 10. Okay, so I got this one in green. Okay. And again, the graph is opening downward. And again, we have with the axis of symmetry. Okay, we have x equal to negative 5. And once again, we have with the vertex. With the vertex, again, we have at negative 5, negative 10. Now, both coordinates are negative. And it is beneath the x-axis, and one might be inclined to think that it is going to be a minimum. But looking at how it is situated with respect to the rest of the x and y values that make up x and y, or h and k values that make up the graph of this quadratic function, that happens to be the high point. And so this particular vertex is going to be the location of this quadratic function's maximum. And okay, so these are key elements. They're introductory, but they are key foundational elements for the characteristics of the graph of a quadratic function. And tell you what, just for the next few moments, okay, let's see what we get for So if we determine again, same three components, the direction that f of x opens, the axis of symmetry, and the vertex. For the following two functions. Okay, so we have the first one, we have f of x is equal to 3 times, okay, the square of x minus 7. And we'll say for the other function, so you have f of x is equal to negative 2 times, okay, the square of x plus 6 plus 25. So for both functions, let's see what we get for the direction that the graph opens, as well as the axis of symmetry and the vertex, and we'll discuss in a few minutes. Okay, for these two functions, okay, the layout is already in vertex form. Okay, and okay, to once again answer these three items, we can go ahead and identify just what the values of A, H, and K will be. Okay, so you have with the case of A, in the first function, so you have A is equal to 3. So you have that A is positive, and with A being positive, regardless of what the values of H and K will be, okay, f of x is nonetheless going to open up. Now for x minus h is represented by x minus 7. So in determining h from x minus 7, again, I'm going to set that expression equal to 0. So I have x minus 7 equal to 0. So we have x is equal to 7. So again, you have x equal to h equal to 7. And so your axis of symmetry is going to be at x is equal to 7. And if you notice, okay, we don't have anything added or subtracted after 3 times the square of x minus 7. So there's a void here. There's kind of like a blank space. So that means here that k is equal to 0. So the vertex hk is going to be on the x-axis, okay, and that is going to be situated at 7, 0. So looking at what we have among the features, for this particular quadratic function. Okay, so if you notice, okay, so you have the graph is opening upward, and again we have the axis of symmetry. Okay, you have this dividing line here. So you have x equal to 7. And again, you have f of x at 3 times the square of x minus 7, so the graph is moving upward. And in the case of the vertex, we have 7, 0. Okay, and this is situated at the bottom, so in this case the vertex is going to be the function's minimum. Right. Now, in the case of what we have with the other function, And here we have with f of x equal to negative 2 times the square of x plus 6, followed by the addition of 25. Okay. So we have for a is equal to negative 2. Okay, so a is negative. So this means this time that f of x is going to open downward. All right, now we have with the determination of h. Okay, so you have x minus h. Okay, you have represented by x plus 6. We have x plus 6 is equal to 0, so we have that x is equal to negative 6. Okay, so that's going to be your h value as well. And again, for the k value, now we have the addition of 25. So k is equal to positive 25. So you have for the axis of symmetry, again, that is going to be at x is equal to negative 6. And for the vertex HK, okay, we have that located at negative 6, 25. I think I have this picture up as well. Let's see. Yeah. Okay, so we have with this particular graph, okay, so we got the vertex again at negative 625. Again, we have the axis of symmetry. We have x equal to negative 6. Again, the graph is opening downward. And the vertex, okay, which again we have at negative 625. Okay, that is going to be, in this situation, that is going to be the quadratic function's maximum. Okay, so like the maximum value would be at y is equal to 25 whenever x is equal to negative 6. Okay, so the vertex is a maximum. Now, just sort of adding on to the underlying pieces in the overall framework with the mechanics. You have not just the vertex, but other points that can potentially make up the graph of a quadratic function. And let's say that just kind of expanding the model. And let's say that if we have we have a quadratic function, and we have that f of x is equal to, say, the square of x plus 4 minus 4. And we were to determine, okay, the following. Okay, so you have, again, just kind of using as the building blocks, okay, the direction f of x opens, the axis of symmetry. Again, we have with the vertex, and also the x-intercepts. And the y-intercepts. And also at least 5 points. At least 5 points on the graph of f of x. Okay, so taking what we have now, okay, so you have f of x equal to a times the square of x minus h, followed by the addition of k. Right. So again, okay, we don't have anything explicitly in front of the parentheses. So have that a is equal to 1. A is positive. Okay, so we're going to have the f of x opens up. Again, x minus h you have represented by x plus 4. You have x plus 4 is equal to 0, so you have x is equal to negative 4. So we're going to have for the axis of symmetry, again, so you're going to have that x is equal to negative 4. As for the k value, we have the k value is equal to negative 4. And with both the h and the k value, again, we're going to have for the vertex, that is going to be at negative 4, negative 4. So we have that h and k have the same numerical value. Okay. Now, for the intercepts, both the x and the y-intercepts, now, we did look at samples of determining x and y intercepts. Now for x-intercepts, you're looking at solving for x while y is set equal to 0. Okay, so we have so you have y is equal to f of x is equal to the square of x plus 4 followed by the subtraction of 4. And again, so we're looking at setting y equal to 0 as we solve for x. Okay, so in this case, we're going to have 0 is equal to the square of x plus 4 minus 4. Now what I can do here, now I could square out x plus 4 and then set this up as a quadratic equation in standard form and solve for x that way through the zero product property. But I'm just going to write this in terms of the square root property of equality setup. Okay, so if I add 4 to both sides, so 0 plus 4 is 4. I have 4 is equal to the square of x plus 4. And I'm just going to rearrange the terms, kind of like go from b is equal to a format to a is equal to b. So we're going to have x plus 4 squared on the left side and 4 on the right. And just borrowing from the page, working with the square root property of equality. Okay, again, so if I have the square of an expression equal to a constant, then that expression is equal to the positive or negative square root of that constant. So we have with x represented by x plus 4, if we go from the square of x plus 4 to just plain x plus 4, and we have 4 representing p, so we have x plus 4 is equal to plus or minus the square root of 4. So we're going to have x plus 4 equal to plus or minus 2. And looking at solving for x, okay, so you have two different directions here. So we have at the lower end, we have x plus 4 equal to negative 2. And at the upper end, we have x plus 4 is equal to 2. And if I subtract 4 from both sides of both equations, okay, so if x plus 4 is equal to negative 2, and I take away 4 from both sides, so we have that x is equal to negative 2 and negative 4, which will be negative 6. If x plus 4 is equal to 2, and I take 4 away from both sides, and we have that x is equal to 2 minus 4, so that is going to be at negative 2. So we have with the x-intercepts, okay, so I have x equal to negative 6 and x equal to negative 2, or as ordered pairs, like in the form of x is 0. So we have the points I have at negative 6 is 0, and negative 2, 0. And for the y-intercept, okay, we have the general coordinates at 0, y. And this time we're looking at setting x to 0 while solving for y. So we have y is equal to f of x. Now f of x is going to become f of 0. For the square of x plus 4, that's going to be the square of 0 plus 4. We have minus 4. So you have 0 plus 4 is 4. That's going to be squared. Take away 4. 4 squared is 16. And 16 minus 4 is equal to 12. So we have that y is equal to 12. So we're going to have, for the ways upon which we can express the y-intercept, we have the y is equal to 12, or as an ordered pair, we're going to have 0, 12. Right. So in the makeup of what we have for this particular quadratic function, and looking at the breakdown, okay, so once again, for the direction that the graph opens, okay, again, you have your a value was positive, so the graph opens up. Axis of symmetry, we have, again, that x is equal to negative 4. Vertex, we have at negative 4, negative 4, since both h and k are at negative 4. So graph opens up. And the axis of symmetry, again, we have x equal to negative 4. Vertex, again, we have at negative 4, negative 4. For the x-intercepts, if I place in coordinate fashion, so we have locations at negative 6, 0, and negative 2, 0. And for the y-intercept, okay, that is going to be at 0, 12. And for 5 points on the graph, And this is, again, this is what we have so far. Okay, so you got a quadratic function. Again, the graph is opening upward. Okay, so you got the vertex. So you have at -4, -4. Now again, the axis of symmetry. We have an x is equal to -4. So you got your vertex. Vertex is a minimum. And if you notice, we have with the x-intercepts, we have a -6, 0 and -2, 0. And we have the y-intercept is at 0, 12. If you notice, you got 1, 2, 3, 4 points specified. And without having to do any calculating, what you can do is that with the axis of symmetry, you can use this as a guideline to establishing a fifth point. And this can be on the basis of like doing the equivalent of counting squares. Okay, so you have like the minimum, the vertex is the bottommost point, and again the axis of symmetry passes through. And again, the axis of symmetry divides up the graph into two equal halves that will mirror each other. So if you go to, say, like on the x-axis, you got -2, 0. You got 1, 2 spaces to the right. Also, the x-intercept you have at -6, 0. So that's going to be 1, 2 spaces to the left of the axis of symmetry. And guess what? If I go up the axis of symmetry, again, had this level with 0, 12. Okay, have like this point on the axis of symmetry. This would be like -4, 12. And with this point level with the y-intercepts, I got y-intercepts going to be 1, 2, 3, 4 spaces to the right. And guess what? If I go in the other direction, I got 1, 2, 3, 4 spaces to the left. And we can say that we have for our fifth point, which is going to be level with the y-intercepts here, y-coordinates. It's going to be at 12. And as for the x-coordinate, 4 spaces to the right of x equals -4 is 0, but 4 spaces to the left, that's going to land at x equal to -8. Okay, so a fifth point among many other possibilities we can have at -8, 12. And okay, so that can be our possible fifth point once again. All right. Now, earlier I said that there will be interchanging between the standard form and the vertex form of a quadratic function. And let me give you just a case here. So I have in here, so you have converting converting between standard and vertex forms of a quadratic function. Again, for the standard form, we have the y is equal to f of x is equal to ax squared plus bx plus c. And for the vertex form, again, we have y is equal to f of x is equal to a times the square of x minus h followed by k. And once again, in both forms, okay, again, to be a quadratic function, a cannot be equal to 0. Okay. And let's say that just in terms of converting between standard and vertex form. And let's say that if I'm looking at converting, let's say a trinomial such as, I've got a couple in mind. We'll say that we have say if I'm looking at converting f of x is equal to x squared plus 6x plus 8 to vertex form and find the vertex. So just for what we have, okay, starting out from f of x is equal to x squared plus 6x plus 8. Okay, so again, this is going to be the standard form. And to get to the vertex form, now we're not going to be doing anything like factoring, but it's going to have a feel about just like some of the stuff like the factoring by grouping. And what we're going to do here is that we're going to separate the variable terms apart from the constant. Separate in the sense of applying parentheses. So I have x squared plus 6x. Those are the variable terms. So I'm going to put x squared plus 6x in parentheses and separate this from the addition of 8. All right. Now to get to the vertex form, I'll have to add a necessary number to form what is referred to as a squared trinomial. And again, a squared trinomial is a trinomial where if you factor, you're going to have the same binomial expression times itself. Okay, now x squared plus 6x plus 8, it's a trinomial, and it can be factored to x plus 4 and x plus 2. But this is not a squared trinomial since x plus 4 and x plus 2, the factors are not the same. Now, in terms of getting to the vertex form, okay, there's a technique that's going to be referred to as the completion of the square. And what this is going to call for, first of all, you look at what items are in the parentheses. Okay, so you want your first term to be like 1x squared, 1y squared, 1b squared, whatever the independent variable you're working with is going to be. You don't want any coefficient other than 1 to be in front of the square term. Okay, so the first term we have x squared, which we want. Now in terms of completing the square, we next look at the first order variable term, which is going to be 6x. And with completing the square, there's two-step operation in this one. We're going to take the coefficient, that is the number that is next to x, and there's a twofold process. Whatever's next to x in the first order, we're going to take half of this and square. So here, half of 6 is going to be 3. And 3 squared is equal to 9. And we're going to work with 9 in the follow-through. So here we're going to have f of x is equal to x squared plus 6x. And the 9 is going to be added inside the parentheses. Now I'm going to get a square trinomial on this, but I want to keep everything in balance with respect to what we had before. I had x squared plus 6x plus 8. But by adding 9 right now, I have x squared plus 6x to what's going to amount to the addition of 17. So I want to perform a bit of a balancing act. So by adding 9, I'm creating a bit of excess by 9 units on the front. So to override the excess, I'm going to take away 9 at the end, because this would put me back to x squared plus 6x plus 8. But instead of going back to the standard form, I'm going to follow through and proceed ahead to the determination of the vertex form. So right now we got x squared plus 6x plus 9. And here we have 8 minus 9, so that is going to be negative 1. Right. Now x squared plus 6x plus 9, that is going to be a squared trinomial. And the k value is already going to be at negative 1. Now for the x minus h part, okay, so for x squared plus 6x plus 9, now x squared, that is already going to be the square of x. Now in terms of where the completion of the square began, again, to get to the plus 9 in the trinomial formation, I had to square out positive 3. And guess what? The number I square out, that is going to appear at the very end . And in fact, so I squared out positive 3. So I'm going to have f of x is equal to the square of x plus 3, followed by the subtraction of 1. And this is going to be your vertex form. So that'll be the result in this one. And just in terms of identifying the vertex itself. Okay. So again, we have nothing explicitly in front of the parentheses. Okay, so you have like your a is equal to 1. And in identifying h, okay, we have, if we set equal to 0, the binomial x plus 3. So we have the x is equal to negative 3. So again, we have x is equal to h is equal to negative 3. And in terms of what we have for the k value, we have that k is equal to negative 1. So it's going to result that for what we have for the vertex, okay, the vertex hk, okay, so you have hk, so that's going to be at negative 3 and negative 1. Okay, and just another little quick instance. So if I'm looking at converting f of x is equal to x squared minus 8x minus 20. To vertex form. Okay. So I have, in terms of laying the foundation, okay, so I have f of x is equal to x squared minus 8x minus 20. Again, if I separate the variable terms from the constant, so we have parentheses around x squared minus 8x You're going to have followed by the subtraction of 20. And crossing over to completing the square. Okay, so I have x squared minus 8x in parentheses. Leading term inside the parentheses, we have x squared. And then looking at the number next to the first order x, so that is -8. And just like what I did with 6 moments ago, take half of it and square. So the number we have at -8, take half of it and square. So half of -8 becomes -4. And the square of -4 is going to be a positive 16. So you're going to have here f of x is equal to the quantity. Okay, so you have x squared minus 8x. And 16 is going to be added. Okay, and let me mention, okay, so if you notice, okay, we have originally x squared minus 8x minus 20. Okay, but by adding 16 relative to the standard form, I'm creating a surplus with 16. So I'm going to override the surplus of 16 by taking away 16 at the end. So right now I have x squared minus 8x plus 16. So this is going to be a squared trinomial. And then we have -20 minus 16. That's going to form the k value, which in this case will be minus 36. Okay, so we have a squared trinomial with x squared minus 8x plus 16. Okay, so if you could factor and find out, okay, what repeating linear factor you're going to have, or you could look at it like this. So x squared is going to be the square of x, and we had form 16, and this originated from having squared out -4, and that -4 is going to reappear. And so for what we will have in the result, okay, so we have the vertex form, so you have f of x is equal to the square of x minus 4 minus 36 and this is going to be the vertex form. Now I'll just mention right quickly, okay, so again, a little history repeating. So your a value is equal to 1. And for your h and k values, if I set x minus 4 to 0, okay, I already got x is equal to 4, and what I have in x, that's also going to be your h value. So I have x is equal to h is equal to 4, and we have that k is equal to -36, and thus it's going to follow that for this particular quadratic function, the location of the vertex is going to be at 4, -36. Okay, so this is just another sampling of what we have with the conversions.